For centuries, mankind has gazed at the night sky, filled with questions about the enigmas of the universe. In the 20th century, scientists proposed the theory we know today as the Big Bang Theory. This theory struggled to answer crucial questions about the origin, development, and expansion of the universe. However, recent research has added even more complexity to this mystery. In 2023, NASA's James Webb Space Telescope made an astonishing discovery. It detected celestial objects that appeared to be older than the universe itself. This revelation has left scientists baffled, questioning the possibility that a star could exist for a period of time longer than the universe itself. Does this call into question our current understanding of the cosmos? Might it require the conception of a new model to make sense of this enigma? These questions and many more will be explored in this video. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel, be sure to like this video, and turn on the notification bell. About 200 light-years away, near the constellation of Asen Lib, lies an ancient star known as HD 140283. The surprisingly high velocity of the star, HD 140283, at 44,800 kilometers per hour gives us valuable clues about its dramatic history. About 1 billion years ago, at that time, our Milky Way, in the process of formation, merged with a dwarf galaxy that served as its home. However, the most amazing thing about HD 140283 is not its speed but its age. The star is among the oldest celestial objects we have had the privilege of observing and has been nicknamed Methuselah in reference to the biblical character who, according to legend, lived 969 years. Initially, estimates placed the age at a staggering 16 billion years, but the most recent estimate put it at 14.46 billion years, with a marginal error of 800 million years. This figure poses a considerable conundrum when contrasted with the age of the universe as determined through observations of the cosmic microwave background, which stands at approximately 13.8 billion years. The question arises as to how a star can be older than the universe itself, which seems impossible at first glance. This paradox has raised questions regarding the age of the star, the accuracy of our dating methods, and ultimately the actual age of the universe, inviting further exploration of these cosmic mysteries. First, it is critical to understand that calculating the age of celestial objects represents a considerably complicated task. Stars like our own sun maintain their temperature and size unchanged for billions of years, making estimating their age extremely difficult. Astronomers rely on subtle changes in the brightness and color of the stars over time, and then compare these measurements to mathematical models that predict how these stars evolve. A crucial indicator for determining the age of a star is its rotation rate. Over time, stars slow down, similar to a wheel slowing down due to friction. By comparing the rotation rates of stars of different ages, astronomers have established mathematical relationships that allow them to estimate their ages using a method called gyrochronology. The star Methuselah is indeed ancient. In fact, it is the oldest star in the universe with an age that we can estimate reasonably accurately. Instead of wondering whether it might be more than 2 billion years older than its surroundings, we can approach the problem from a different perspective. Is it possible that the universe is not as young as scientists initially believed? Indeed, it is difficult to comprehend the immensity of 13.8 billion years. If we try to summarize the entire history of the universe in a cosmic calendar, where the Big Bang would be equivalent to the most dazzling New Year's fireworks, the Earth would only join this cosmic celebration at the end of the year, while recorded human history barely spans the last 10 seconds of December 31st. Scientists determine the age of the universe by observing the light from stars that were born hundreds of millions of years after the Big Bang. As the universe expands, a phenomenon known as the redshift occurs. When we evaluate both the observable distance and the universal expansion, a universal age of approximately 13.8 billion years is deduced. However, recent discoveries by researchers at the University of Ottawa raised the possibility that the universe is significantly older, estimated to be about 26.7 billion years old. University of Ottawa physicist Professor Rajendra Gupta presents a theory that merges Swiss astronomer Fritz Zwicky's 1929 theory with novel ideas. This theory suggests that protons lose energy during their journey over vast distances and times. Despite being in contradiction with observable data related to redshift, Gupta proposes that by allowing this theory to coexist with the expansion of the universe, we could reinterpret the redshift as a hybrid phenomenon that is not exclusively due to expansion. This reinterpretation would increase the estimate of the age of the universe and could offer explanations for long-standing cosmological questions, as well as some recently raised by NASA. NASA's James Webb Space Telescope has been instrumental in arriving at this estimate of 26.7 billion years. Gupta combines the tired light theory with the concept of evolutionary interaction constant originally proposed by theoretical physicist Paul D., implying that interactions could have undergone changes over time. It is relevant to note that scientists have previously revised the age of the universe on different occasions. For example, in the 1920s, Edwin Hubble claimed that the universe was only 2 billion years old. However, over time, our estimates have improved significantly, doubling the age of the universe. This increase represents an important milestone as astronomers strengthen their understanding of the universe's age, as reached in Gupta's work. Regardless of whether we consider the recorded history of humankind to be equivalent to only 10 seconds or 5 seconds in the immense time frame of the universe, what is undeniable is that the universe is an extremely old and amazing place. Its constant expansion leads us away from previous notions about its age. However, there are also remarkable observations concerning our own galaxy, the Milky Way. Recent measurements suggest that stars in the outer regions of our galaxy move at a much slower rate compared to stars in similar locations. This raises a couple of possible explanations for this phenomenon. One is that our galaxy may possess an exceptionally low amount of dark matter, an invisible substance that plays a crucial role in the gravitational structure of cosmic objects. The other possibility is that our understanding of dark matter, including how much of it exists in the universe, may be mainly different from what we have considered so far. This conundrum originates from data collected by the European Space Agency satellite, which provides detailed information about the positions of nearly 2 billion stars in the Milky Way. This data has led astronomers to reconsider their assessments of stellar behavior, particularly in relation to stars in the outer part of our galaxy. The speed at which stars move is an essential indicator for estimating the mass of a galaxy, since the gravitational force affecting each star depends on the total mass of the galaxy. A recent study based on data collected by the Gaia satellite calculated that the combined mass of our galaxy, which includes gas, dust, stars, and dark matter, is approximately 200,000 billion times the mass of our Sun. Although this figure is considerable, it is about 5 times less than previous estimates. This is due to the fact that the amount of visible material in the Milky Way has not inexplicably decreased. A suggestive interpretation of this result is that there may be less dark matter than previously considered. However, measuring the mass of a galaxy is a notoriously complicated task, raising the possibility of uncertainties in the data collected by the Gaia satellite or in the new analyses that have been developed. The complexities of cosmic measurements extend beyond the age of stars and galaxies. For instance, the distribution and behavior of dark matter remain elusive yet crucial to our understanding of the universe's structure. Dark matter, which does not emit, absorb, or reflect light, is detectable only through its gravitational effects. Its presence is inferred from the way galaxies rotate and how light from distant objects is bent around massive clusters of matter, a phenomenon known as gravitational lensing. Current studies suggest that dark matter constitutes about 27% of the universe's mass-energy content. However, our models of dark matter are still incomplete, and new theories are continually being proposed. One such theory suggests that dark matter might consist of a variety of particles beyond the commonly considered WIMPs, weakly interacting massive particles. For instance, axions, which are hypothetical elementary particles, are being explored as potential candidates. Moreover, the acceleration of the universe's expansion, attributed to dark energy, continues to challenge our theoretical frameworks. Dark energy is thought to drive the universe's expansion at an ever-increasing rate, contributing approximately 68% to the universe's mass-energy content. Understanding both dark matter and dark energy is essential for refining our models of cosmic evolution and potentially unlocking new physics beyond the standard model.